Hi everyone, this is our first Haskell video, and today joining me is Aman and Monica, so I'm just going to let them quickly introduce themselves.
Yeah, so hi everyone, my name is Aman. I'm a grade 11 student studying at Dubai College, and yeah, I live in Dubai.
Hi everyone, I'm Monica, and I'm also in 11th grade going into 12th grade, and I'm from Cambodia.
Yeah, and today we're just going to go over like a quick crash course in some of the basic functions of Haskell. And for simplicity, we're just using a Haskell environment and Replit, and we can put a bunch more details of how to set up your Haskell environment in this video description. But for right now, I'm just going to let Aman take it away with some of the introductory details of Haskell.
Yeah, so as Rohan explained, what I'm going to do is just show you some of the basic properties of Haskell. So pretty much the starting thing that we do on every coding language is, the basic operations, adding, multiplying, subtracting, and dividing. So on Haskell, this is really easy to do. So in the terminal, under GHCI, we can just easily, add two numbers. For example, if we had 1 plus 1. Yeah, so that gives you a value of 2. Yeah, just another example, 2 plus 2, that is 4. So that only works if you have the same type on either end. So because it's an addition sign as well, it needs to be two integers on either side. So yeah, if you put a string plus a number, then it wouldn't work. Yeah, and if we were to subtract two numbers, for example, 1892 minus 1472, that would return the subtraction of the two numbers. So in this case, that's 420. Same concept with multiplying. So we can do 10 times 10 as well. And as you might know from other coding languages, the multiplication operation is done using an asterisk. So yeah, this returns 100. And if we were to do 5 divided by 2, it returns a float because in Haskell, you can, like integers are quite integrated with floats as well. So if you were to do divisions, it also returns floats without throwing any, errors or anything like that. Yeah.
Yeah, and one thing I'll just quickly add is since Haskell is a functional programming language, we actually represent everything in functions. So there's like an add function, a subtract, a divide function, multiply function you could also use to do these operations. But what's happening here is we overload those functions with these symbols, and then we use them in between the numbers. So it's more familiar to what we're to what we're used to. But there are actually explicit functions you can call to do all of these things as well.
Yeah. Yeah, cool. Yeah, so yeah, as with any coding language as well, there's precedence. So with parentheses, for example, that the operations or the stuff inside the parentheses are going to be run first. So for example, if we had in parentheses 50 times 100 minus 4999, if you work it out yourself, 50 times 100 is 5,000. So it does the stuff inside the parentheses first. So basically what we're doing here is 5,000 minus 4999, which is 1. Yeah, and then yeah, so it also reads from left to right. So in fact, because it is on the left, if we were to do the same thing without the parentheses, it would return this. Oh, sorry, I included the wrong numbers. Yeah, so if we were to do the same thing, it would return the same value. But if we just change it around, change it a little bit, if we put this parentheses second, then it would.
Oh, you accidentally typed in, yeah.
Yeah, sorry. Oh, this space. Yeah. Yeah, so as you can see, it does the right-hand side operation first, and it returns a completely different number. Cool. So now, apart from basic operations, there's also Boolean algebra. In standard practice, double ands are for the Boolean and then two like vertical lines is for or. and there's also the not. So you might have seen that as well in other programming languages and just like basic computer science. So we can just test that out. So true and Boolean and false, that would return a false. It's pretty much doing 1 and 0, which would return 0, which is false. True and true would return true. So yeah, you get the gist of it. That's how it works. Same thing can be done with or. Yeah, works. And with not as well. So that just inverts. Oh, sorry. The values. So we should get a false. Yeah.
Yeah, and not there is a
Okay.
function, but so one thing that's different about Haskell than other programming languages is we don't actually have to surround the arguments of a function in parentheses. So Aman, maybe you just want to rerun that, but without the parentheses, just to show that it will still work. Although actually, yeah.
Yeah, so you get the same value with or without the parentheses. So yeah. Yeah, so this same kind of process is true for equality as well. So if we're so for example, if we did 5 is equal to double equal to 5, that should return a true. So in this case, obviously the integer 5 is equal to the integer 5 on the right hand side. So it'll obviously return a Boolean true statement. 1 is not equal to 0, so it would return false. Yeah, and this also works with strings as well. So if I were to have hello, then it should also return true. Oh, sorry.
You just forgot the one of the quotations. Yeah, so that's just like in most other programming languages where 2 equals is for, oh, that's an assignment, but 2 equals are for equality and 1 equals for assignment. So that's also pretty similar to most other programming languages.
Yeah, so we got true. As I think I spoke about before, we can't do 2 different types of data types with the addition function. So if we tried to do 5 plus a random string, 5 plus 5, for example, it would throw some sort of error, which, yeah, so that obviously implies that we can't do different kinds of operations with different types of, with different data types. So this works for other data types as well, like characters and lists and all of those sorts. Yeah, cool.
Yeah, so I guess I can sort of take over now and talk a little bit more about functions, which, as the name functional programming might suggest, are a really important part of Haskell. So just to quickly go over, Aman showed this earlier with the not function, but when we have a function in Haskell, we just say the name of the function, and then we give it 2 arguments, 2 or more arguments, or actually it could just be 1 argument. We give it some list of arguments, which are just separated by spaces, which is unlike, for example, in Python, where you have parentheses and commas between the arguments. That's not really how we write out functions in Haskell when we evaluate them. So in this case, we're just doing a min function to get the smallest number. We could do the same thing with the same arguments, and now we get the other number because that's the maximum. And so another interesting thing about Haskell is we define functions and variables the same way. So Aman showed us earlier that we could define a variable like this with a value. We can also define a function in the same way. So we just say the name of the function, what we want it to take in, how many variables. So this is a function of 1 variable, but we could also make a function of 3 if we wanted. And then we can just say what we want the function to return. So one thing you might notice is there's no return keyword like there may be in Python or another language, because Haskell just knows that whatever we type in here is going to be the return value. So we can just save this file, and then back in the REPL, we use a load command, which we just abbreviate :L, and then type in the name of the file. And now our function exists here. So when I put 1, 2, and 3 to F, it adds them and gives me 6, which is obviously what we would expect. And we can do other things like this too. For example, I can add the output of two different functions, and that should work just as expected. And so we can make these functions more complex as well. For example, adding in an if statement, maybe. And in Haskell, we usually don't try to use if statements because it's not very idiomatic in functional programming languages. We try to do stuff like pattern matching. But for this introductory video, we're just going to show how you would write something with an if statement. So for example, we could do if x plus y is greater than 10, then let's see, then return x plus z, else return y plus z. So you'll notice that we actually do have a then command. In some languages, we just say if and then say what we want it to do. But in Haskell, we have to actually add in a then command. We can reload the file. And now I'll say, let me try and give it a condition where this is true. So x and y have to be greater than 10. So I'll do 10 and 10, and then just put 1. So it adds x plus z in this case, which is 10 and 1. And if it's less than 10, so 1 and 1, 5, then it adds y and z, so 1 and 5, 6. So that's a way you can define functions in Haskell using, for example, if statements. Now, another important thing in Haskell are lists. So because Haskell is a very typed language, we can only have lists with the same data type, which is against a language like Python, where you might be able to have a string and then an integer and then a Boolean value. So if I try and do that in Haskell, though, it will give me an error because it doesn't know what it should have as the type of this list. Should it have as the type of a string or an integer or Boolean? It's not able to decide. So we actually just have to put the same thing, same type of objects in all of our lists. So here are some examples of operations we can do on lists. We can join two lists together. So we just do a double plus operation for that. Oops, I forgot a bracket. We do a double plus operation, and that just joins those two lists together. Another cool thing is that we can actually do this with strings as well, since in Haskell, lists are just strings of characters. Oops. Hello world. So we just added together those two strings of characters, or lists of characters, which are strings. And then we can also add, so this is how we add two lists together. If we just want to add an element onto an existing list, for example, we have a character and we want to add it onto an existing list like this, then we can just use this colon, which stands for the cons operator. So it does this concatenation of this single element onto the existing list. And there are some slight differences in which is more efficient to use in which case, but since we're just going to keep this to an introductory video, we won't go over those right now. We can also index lists. So indexing a list actually happens with the double exclamation point operator, which is a pretty unique operator as far as programming languages go. I don't think it's used as an index operator in any other languages, at least that I know of. So as you'll see, Haskell is 0 indexed because 0 gives us the first element. And then just to check that again, 1 will give us the second element, which in this case is 2. And so another interesting thing about lists is we have operations that sort of implicitly map over them. So if we take this example, we're doing a greater sign operation, greater than operation over these two lists. So it checks if each element is greater than the other. In this case, 1 isn't greater than 2, even though 2 and 3 are greater than their respective counterparts in this list. So we get a false. But if we try this instead, we would get true because each element in this list is greater than each element in that list. And of course, we can do the same thing with other sorts of operations as well. So in this case, it will be false because 3 doesn't equal 4. But if we try it with the same list, then we will get a true value. So before we move on to some other cool things we can do with lists, I just want to go over a quick tour of all the cool functions we can use on them. So we can get the first element of a list with the head function. And we can get the tail of the list with the tail function. And the tail is just everything that's left after the head has been removed. We can also get the last element of a list. And all of these functions are really important in functional programming, especially when we want to solve problems in a functional way. So we can get the length of a list. We can reverse a list. So all of these pretty much do what you'd expect. Another set of really important functions in functional programming languages are the take and drop functions. So I can take the first element of a list, or let's do more than one, the first three elements of a list, or I can drop the first three elements of a list, and that will just give me the last element. So I'll just get 4. But in this case, notice it's not the element 4, it's a list of 4, because take and drop still always return lists. So we can also get the sum of a list, just adds all the numbers together, or the product. In this case, it would just be a factorial. And so those are just, there are a bunch of other functions, but those are some of the basic bread and butter functions you need to play with lists. And so before we move on to list comprehensions, I just want to show you one really cool thing about Haskell, which is that in addition to being a functional programming language, it's a lazy programming language, which means we can actually deal with infinite quantities, which is something that's super cool and allows us to solve problems in really cool ways. So before we get to infinite quantities, though, I just want to show you another one of my favorite features of Haskell, which is this really cool notation it has for ranges of numbers. So I can just type brackets 1.20, and that's saying the range of numbers from 1 to 20. Or I could do something like this. And now it sort of increments each number by 4 to get to 20. So I just gave it this simple pattern, 1, 5, and it realized that what I want is adding by 4 in steps of 4 to get to 20. And so that's what it did, which I think is super cool. It's just really concise notation for this. And so now that I've said that, you could also imagine doing something like 1 ... and just never giving it a final value. And that's actually a valid thing. It's a valid thing to say. I'm not going to do it right now, because if we do it, it will obviously crash the REPL, because it will try to compute an infinite list. But we can have these infinite lists in Haskell because it's lazy, which means that we can have these infinite objects around and just never compute the entire object and only take what we need from it. So I can show you something like this with take 10 of repeat 5. So if I do repeat 5, it will give me an infinite list of 5. But in this case, I'm not trying to get the whole list. I'm just trying to take 10 from it. So in that way, I can create this infinite list without computing it, and then only take the bits of it I need. I can also try and do the same thing with another infinite list sort of function, which is cycle. And so in this case, instead of giving it a single element, I give it a smaller sublist, and then it cycles that into an infinite list. So cycle list of 1, 2, 3 represents the list 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 forever. But again, I only want the first 4 elements. So I get 1, 2, 3, 1, 2, 3, 1, 2, 3, and that's 3 full cycles. And then I just get part of the last cycle. So this infinite list capability is really cool in Haskell. It's something I personally love. It's one of my favorite features of the language. And it's something that is especially in a lot of functional languages, but especially in Haskell, we can use it to solve problems in really elegant ways. So now that we've gone over some basic list operations and infinite list things, I'm going to hand it over to Monica to talk to you guys a little bit about list comprehensions.
Okay, yeah, so the last thing we'll cover for today are list comprehensions, and just extending from that tuples as well. But yeah, if you're familiar with set comprehension in math, this is pretty much the same-ish thing. But with list comprehensions, there are 3 main components to it. The first is the output, and then the input sets, and then the predicates or conditions. So I'll go through a couple of examples while talking about it, just to sort of illustrate what's going on. Be right. No, I did that twice. Never mind. Okay, so if we take a look at this, we can see that it has an output, which has a function applied to it. So in this case, it would be 2x. And then this one also has one input set, which is just the set from 1 to 10. And then if we were to run it, it will generate a list, which takes in all of the elements within the input set that we have, and then multiplies it by 2. What we can also do is add predicates into the list comprehension, like this, for example, where we only select elements within the input sets where twice the element is greater or equal to 12. So if we were to run it, then we will get elements that exactly satisfy the predicate. This is another example of a list comprehension with predicates as well. This is using modular arithmetic, but yeah. The cool thing about this is we don't only have to have one input set or one predicate, we can have multiple. So an example of a function of a list comprehension with multiple predicates is this, where we have that, yeah, it will take elements from the input set between 10 to 20. And then it will print out only the elements that are not 13, 15, or 19. So that's what it's doing here. Another one that utilizes several input sets is this. Okay, I don't think I'm copying in that correctly. Wait, okay. Yeah, never mind. So something like this, where you have two input sets, X and Y. And then what Haskell will essentially do is sort of like run through all possible combinations from these input sets. So if you're familiar with the notion of Cartesian products, this is essentially like just generating the set of Cartesian products of X and Y and inputting it, like inputting the elements into our list comprehension. And if we run it, then that is what we will get with the predicate as well. By the way, the process of weeding out like lists with predicates is also called filtering. Other cool things that we can do is incorporate like if-else statement, which we can put in the output as well as incorporate it as a predicate. So an example of this is here, where we define a function where if we have a number like X is less than 10, then we print boom, else bang. And then we will take the X values from a list that we will put in. Yeah, so if we let that run and then we call the function on our input set, we will just get a list based on the list comprehension we defined. Last thing is that we can also run nested list comprehensions, which is similar to Python as well, without flattening the list itself. So let's take an example. We can start by defining a nested list as such, and then we can call a list comprehension like this, where what it'll do is just iterate through every single list within this list and take out only the even elements, but still preserve the nested structure of the original list. Some more kind of silly examples, but I guess it's pretty illustrative of like the power of list comprehension are these. So we just define a couple of lists first. In this case, it would just be like combining nouns and adjectives in, yeah. And then define.
Yeah, and the reason we can still use strings is because we represent them as lists of characters. So like when we say list comprehensions, we mean lists, like you can put any valid list to work with them.
Yeah, that I don't think that printed nicely, but
yeah.
Never mind. And maybe another example list comprehensions is this. So, okay. So here we're just defining a function that we sort of embed a list comprehension into. So now we're calling list tuples with 3 input sets. And so let's just quickly just write something up.
Oh, it just, you forgot the S when you wrote out the.
Oh, okay, never mind.
That's a nice thing about Haskell. Its errors are usually pretty easy to understand, which other languages not always true.
Yeah. So yeah, I think this example in particular shows like pretty nicely how it's kind of iterating through every single possible combinations of the inputs from each of the input sets. But yeah, that's I think all for list comprehension. If you guys don't want to add anything else.
I just add one quick thing, which is like, so we're just showing like a bunch of funny, like interesting examples of list comprehensions, but like one of the really cool things is just like how how concise they let us be in Haskell. And in general, we can be super concise in Haskell, even beyond list comprehensions. So this is an example that there is in the book that I just want to draw your attention to really quick, which I think is really cool. So it's just showing like how easy it is to define a length function. So I think we can appreciate it more if we almost like imagine the Python syntax. So if we have some list, to define a length function, we sort of need to initialize the counter first. And then for each element in the list, we need to increment that counter. And then we can finally return the counter at the end, something like that. So in Haskell, what we could just do is we could create a list comprehension. We can go through every element. And in this case, we usually say what we want to assign the element to. So XS is the list we're giving to the function. And so usually, like in the examples Monica was showing, we define a variable. But here, we don't care what that specific value is. We just return the same thing every time, which is 1, because every element is just worth 1, like when we count. And then we can just take the sum. And so in like one line, what we do is we define a length function. So just check that it works. Should give 10. So I don't know. I just think that's super cool. Like this is how concise and brief we can be in Haskell. And like Monica was saying, there's like when she was describing list comprehensions, how they're basically just set notation. So much of Haskell is just math, and like taking math and making it into a programming language. So a lot of this stuff is everywhere, and I think it's really cool. So I just want to show that example quickly.
But yeah, I definitely agree with like basically it being math. It seems that quite a bit walking through it, and that's pretty cool for me. So yeah. Now we'll just move on to the last topic, which is our tuples. So before we kind of introduced the notion of lists, and tuples are in some sense similar to it, but also very, very different. I think there are a couple of main distinctions we should make before we show too many examples. But so the tuple has types, and its type is going to be determined by its components. So the number of components as well as the types of its components. This makes tuples have a very, very rigid structure. And so, yeah, tuples are useful when we know exactly what type of data and how much of it we are going to use. Also, we did note that lists have to have the same types in its elements, but tuples do not have to follow the same principle, so they're not homogeneous. Also, yeah, like lists, we are also able to compare tuples against each other, but again, it must also be of the same type, which is just the same number of elements, I guess. There was one last thing I forgot to. Okay, whatever. Oh yeah, so whenever we define functions with tuples, it's not as easy and flexible to work with as functions that involve lists. So everything that we do with tuples, it kind of has to be of the same type. And then if we want to extend the type or manipulate it, then we have to write very specific functions to do so. So let's say we want to extend like a pair to a triple, then there needs to be one function for that. And then if we want to extend a triple to like a 4 tuple, then there has to be a different function for that. So they're all very specific and rigid.
Yeah,
anyway,
there's not
so
like
I'll just
there's not just like a standard like append function like there is for lists. And that's because, just like Monica said, like for a list, the type is integer, which just means a list of any number. Like it could be an infinite list of integers or a list of 1 integer. But for a tuple, if it's 2 elements, it has to be int. If it's 3, it has to be int. So like that's how the computer represents it. So like that's what Monica was saying there. Just another way of thinking about that.
Yeah, so I'll just go through like a couple of important functions for tuples, which are not too much, but yeah. So the first one is FST, which just returns like the first component of a tuple. This is a built-in function into the language, but it's specifically for pairs. So 2 tuples with 2 elements. So let's say we have 8 and 11. If we run it, it'll just return 8, which is what we expect. Let's try another tuple that has different types as its elements. again, it will just return the first element. And if we were to try it with like a triple, yeah, it doesn't work because this function is specifically defined for pairs. So you can see again how rigid it is to work with tuples. But again, there's also benefits. The second one is just S and D, which returns the second component in a pair. So let's 2 and 10. I'll just, oh, forgot to close it. Okay, yeah, so just return 10.
Oh, you just didn't capitalize the F,
Okay.
I think.
Yeah, I think that's the case.
Yeah, it works now.
Okay, yes. Yeah, so if we are able to define specific like functions for tuples as well, but we're not going through that today because we're still in like the basics of it. But this is just to introduce the concept. The last the last function to do with tuples is zip. So it's just taking two lists and zipping them together by like matching elements, which is just joining elements of each index that we have into pairs, so into two element tuples. So let's do one with an example. So as you can see, this is just zipping together 1 and 5, 2 and 5, etc. Into tuples, which altogether form a list. Let's look at another one. Again, this is pretty much doing the same thing. Note how we can have different types within the tuple as well. But then within the list, if you look like, yeah, you can see how the list contains only one type, which is a tuple with the integer as its first component and a string as its second. Okay, last example. So what happens if we were to zip two lists that don't have the same length? Well, it'll just sort of be limited by whatever the shorter list is. So as you can see here, it stops at the third element because our second list only has 3 elements. What we can also do is zip finite lists with infinite lists. So let's take this as an example. So here we can see that the first list is pretty much all the natural numbers, and the second is just a 4-element list, and what we get is just a 4-element list as well. Lastly, I want to just show a pretty cool combination of list comprehension and tuples, where
Yeah.
I guess, yeah,
Oh, sorry.
the
And
aim of it.
Sorry, while you put that
Go
in,
ahead.
just to like remind people. So the reason that infinite lists work again is because we don't actually compute them. We just like treat them as infinite objects, and then we just take what we need, which in this case is just 4 elements, and then we discard the rest. So like for me at least, this was a super confusing concept when I first tried to learn it, because it's like weird to think that the computer is dealing with infinite like length things, but it's really just like, it's really just an illusion. Like it's not, if it tried to do the infinite thing, it would like you expect break. So just to remind everyone of that. But Monica, you can pick up.
Yeah, so this is just trying to generate, I guess, sets of the side lengths of a right angle triangle that adds up to 24. I'm not going to break down too much like the layers that go into this, but I just want to show the power of that. So if we run right, it'll give us the output, which also satisfies all of our predicates. But yeah, that's a pretty cool application of both list comprehension and tuples. And I think that's all for me.
Yeah, so that's like a quick like whirlwind tour of Haskell. These are a lot of the things you're going to be working with in Haskell, lists and list comprehensions and functions like we were talking about, take and drop and stuff like that. So this is going to be like a good base for things you want to do in Haskell in the future. So for our next chapter, we're going to dive a lot more into Haskell's type and type system, which is really what makes Haskell like so distinguished among other programming languages, because these are a lot of things like general functional languages can do, but Haskell's type system is really powerful, and it lets us do a lot of cool things that we can't do in other languages. So that's going to be really exciting, and we hope you'll join us for this next video, which will be released next week, since we're going to be releasing videos every week. And while you're certainly welcome to just use these videos to learn on your own, if you're interested, we also hope you'll check out the Paradigm Conference, which is what all these videos are directed towards, because we definitely love to have you participate in the Haskell track or a different language track if you're more interested in a different language. So I think that's all for me, unless any of you guys wants to end anything, or we can just wrap it up. Okay, that's it then.
No, I just want to add that I think Haskell is really beneficial and it's really easy to learn as well. So like all of the examples shown here are very similar to other languages as well. So I think a lot of the participants of the Paradigm Conference and people who are just interested in Haskell who are going through the videos will probably not have that much difficulty learning it. So yeah, so I think Haskell is definitely really cool, and yeah, you guys should learn through it.
Yeah. Okay. Then I guess we'll see you all next video, and thank you for joining us.
Thank you all.
See you guys.